Welcome to the demo of the NeoGlia Federated Learning Platform. This is a package that we've built to showcase our product as an MVP to pharmaceutical companies when we were pitching to their data scientist teams. This allows researchers to connect to data sets that are behind the hospital's firewall and train distributed or federated deep learning models on these data sets. In the demo itself, we have 3 data sets mimicking 3 real-life hospitals. In particular, we have the eICU dataset, which is a famous intensive care unit dataset that is pulled together from dozens of US hospitals and made available by MIT. So this dataset was split up to emulate 3 hospitals, and the 4th server is the hub. So the hub is the server the data scientist of the pharmaceutical company would interact with, and the 3 hospitals are the guardians and the source of the data. And in the federated learning regime, what happens is that the data scientist defines a model and the parameters of an experiment, and then this configuration gets distributed to the hospitals. The hospitals then train a local model. So let's say the data scientist specified that she wants to train a model on predicting mortality in the ICU units, and she wants to model the probability of a patient dying in the first 24 hours. This model and configuration was sent to the hospitals, and they begin to train independently and locally. So once they've done this, they send back the weights of their model to the hub, but notice that only the weights are leaving the hospital and the sensitive patient data remains behind the firewall. Then these models are averaged on the hub. So H1, H2, H3 models are averaged to become the average model. And this is then sent back again to the hospitals to continue their training. In essence, this is the federated training regime that allows us to train models without moving data out from sensitive places and learning something very powerful and accurate without actually peeking at the data itself. So once this process has iterated far enough or long enough, we will end up with a model that in the limit is as good as if we had access to all the data in one place pulled together. So just to demonstrate that this is a real demo, here we have the actual servers on AWS running for us. So the 3 hospitals are served by 3 T2 large EC2 instances on these IP addresses, and the hub is running on this address, and again that's an X large instance as well. So these are regular EC2 instances with NeoGlia's federated learning package pre-installed on them for communication and model training purposes. And so now on to the demo. In this MVP, we have implemented 3 different ways to showcase the package. We have a classification, a regression, and an imaging dataset. So in this very short video, I just want to go through the classification and the imaging examples. So we will use the eICU data, so collected from patients in the ICU units of these 3 hospitals, to try and train a model that is able to tell whether a patient is likely to die in the first 24 hours or not. So this is a common model type everyone is interested in intensive care. We want to triage our care and resources and attend to the needs of the people who need it most. So if we have a model that can reliably and quickly tell us which patients we should focus on, obviously that's going to save lives and also save resources and money to the hospital. So in this model, we start by importing everything in the Neoglia Federated Learning package, initiating a few starting variables. And then first off, we will have to connect to the hospitals. So this is all done. And now we can actually query these hospitals and ask them what sort of data they have. So let's ask hospital 2 to list its data sets. And we immediately see that it has an imaging data set, it has a classification data set, and it has another data set that is meant for a regression problem. And we can do the same for all the hospitals, obviously. Now, the way we structure this product is to allow data scientists to do what they usually do. So all of this is working in a Jupyter Notebook environment. Nothing has to be altered in terms of designing models and doing exploratory analysis, etc. We just provide a few helper classes and let the data scientists carry out the research they would usually. So one crucial object is the learning config, which is basically a wrapper object that pulls together all the information about the experiment. So in this experiment, we need to define what is the data set we want to train on, what is the data set we want to test on, what sort of batch size we should use, how often we want to do the averaging of the federated learning, what is the performance metric we want to use, etc., etc. So as you can see, all of the Neoglia package components come fully documented, and you can very easily find out what each of these components are expecting and doing. So let's actually instantiate this learn config object with a predefined config file. So we will train on the classification dataset, and we will train with a PR curve and accuracy as our performance metrics. So the next step is to define the model, and what is quite attractive about this product is it allows full flexibility. So here, just for convenience, we imported a feed-forward neural network, but if you check the source code of this is nothing more than pure PyTorch. And in fact, you can implement and use whatever model you want. So you can federate and send any model you want to these hospitals. The next stage is actually pulling everything together. So the learner object is instantiated with the config, the model, the loss function, and crucially the 3 hospitals we want to train on. And now that everything's set, we can start the learning process. So now what happens under the hood is the model specification, the configuration specification has been sent out to the hospitals. They receive the configuration, they select the requested data set for training, they set up the model for training, and they start training. So due to how we set this experiment up, first each of the sites will do 10 rounds of local training, and then we will pull together their weights and average them. So we should see how the model is doing after 10 epochs. But until then, we can switch over and check what are these servers are actually doing. So we have Hospital 1, Hospital 2, and Hospital 3 connected via terminals. So for demonstration purposes, we can very easily see if they're actually doing any computation. So just as a reminder, these are the EC2 instances we saw earlier. And as we can in fact see, they are communicating through a WebSocket with the hub, and they are carrying out work as they are training the model. So you can see the 2 CPUs of each of these nodes spinning up and down, and the memory utilization going up and down. This bottom right terminal is hooked up to the hub, and it's actually showing its network logs. So we can see how the hub is communicating with the 3 hospitals via WebSockets. And this is so that the hub can receive the updated weights and send back the averaged model every 10th iteration. Switching back to the notebook, we see that after the first 10 iteration, the hospital 1, 2, and 3 are producing precision recall curves that are less than ideal. So a perfect precision recall curve would pretty much touch the top right corner of this graph. And the aim of the training is to maximize the area under the curve by pushing it to this top right corner. Now, what's interesting is that the average model, even after 10 rounds, is already better than any of the models on their own, which again goes to show the basic premise of deep learning, which is the more data you have, the better your model will be. So just to recap, what happened here is these 3 sites trained their models, then sent their weights to the hub. The hub then averaged those weights and produced this average model here. Then this average model was sent back to the 3 sites, and the 3 sites continued with their training. And quite amazingly, what happens is that 10 rounds later, the models from these sites are a lot better than they were. So as you can see on the PR curve from hospital 1, 2, and 3, they've made huge progress, and you can see this in the area under the curve as well. They used to be around 50%. And this process of iterative training and sending the weights back and forth while preserving patient privacy continues until the model converges and we can stop. Just in the interest of time, I will stop this training process and very quickly showcase the imaging demo we also have set up. So just as before, we import Neoglia's package and connect it to the hospitals. So we're going to use an imaging dataset, but not a medical imaging one, just a toy dataset. And in imaging deep learning research, the MNIST dataset is the workhorse that everyone uses for these demos. So just as before, we define our config file, etc. So the interesting thing in this demo is the MNIST dataset is a handwritten digit dataset going from 0 to 9. So each image is a single digit, 24 by 24 pixels. And the way we split this dataset up to make the federated model's job a lot harder is that hospital 1 gets digits from 0 to 2, I believe. Hospital 1 gets digits from 3 to 6, and then hospital 3 gets the rest of the digits. So this means that there is basically no overlap between distributions in training data. Yet, as we will see, even in this extreme scenario, through federated learning, we can learn a global model, which is quite remarkable, really. So let's start the process. And just as before, we have done the same. We set up our config, we've set up our network. Our network in this instance is a very simple convolutional neural network. But as before, you can specify your own and make it as complex as you'd like. So just as before, we trained the models on site for 10 iterations or epochs, and then we will average the weights on the hub and send back the averaged model. What is going to be very interesting is how these models will learn from each other to recognize all of the 10 digits. So we're coming up to the first evaluation round. The weights are sent back to the hub, and we'll soon see the results. Beautiful. So hospital 1, as I said, actually got digits 0, 1, 2 and 3. Hospital 2 got these 3 and hospital 3 got the last 3. And you can tell that just these models on their own are doing pretty badly, right? So they are misclassifying all of the digits they haven't seen in the training data set. And that is not a surprise. That is completely expected and acceptable. What is remarkable, however, is that once we average these 3 models, already the average model is not doing too bad, which is evidenced by how on the confusion matrix most of the predictions line up on the diagonal. So quite remarkably, as the federated learning proceeds further and iteration after iteration, the average model gets sent back to the sites, they will become remarkably good at predicting digits they don't really have in their own hospital. So as you can see, hospital 1 is, instead of just confining its predictions to the first 4 digits, which is basically its training set, is now quite confidently sometimes classifying digit 9 as a 9. Sometimes, quite interestingly, it misclassifies it as a 4. This is quite remarkable. Translating this into a healthcare setting, what this means is that the data scientist of the pharmaceutical company gets to train a model on patient populations that are not even overlapping. Now, obviously this wouldn't really happen in the United States, where there's a fairly good mix of various classes across the country. But you can imagine if the pharmaceutical company wanted to train a global model where, let's say, the genetics of the patients might be widely different between different parts in the world, you could see how a global model could be trained even without pooling the data together. So let's see how the model is doing in the 3rd iteration. You can already see hospital 3 has basically learned to classify all 10 classes. Again, hospital 3 doesn't have training data, but only from class 7, 8 and 9. Yet it manages to classify these other classes perfectly as well. So this is the magic of federated learning, that we can learn these global models without having to pull the data together from these different locations. And by doing this, we get to preserve patient privacy and also allow researchers to learn something meaningful and new and predictive from healthcare data. So this was the MVP that we've built with NeoGlia, and thanks for listening.